Okay, I think we'll get started. So today we're going to talk about the ideal gas law. And in my experience teaching, this is something that students pick up very quickly, and then it, for some reason, sticks in our brains for a long time. So I'm going to let most of the burden of this fall on you and working the problems in whatever Gen Chem book that you have. So I think that if you work a bunch of problems until you feel really good about the ideal gas law, and then the ideal gas law in the context of gas phase chemical reactions, you'll have it down, and you'll have it down. You probably won't forget it the rest of your life. So it's just one of those things that really stick with us. All right, so just to kind of go through it, and then I'll try to say some things that maybe we want to be thinking about that might not pick up when you're just working problems. So the ideal gas is predicated upon the fact that in a gas, the molecules are very far apart. And if you remember back to when we did the physical kinetics, we saw that the mean free path is much, much longer than the size of a given gas particle. So the gas spends most of its time moving about the container and very little of its time colliding. And so what the ideal gas says is that we're going to just ignore all of the interactions. So if two gas particles are coming, ideal gas particles are coming at each other, they just pass right through each other. So not even elastic collisions between them. There's just nothing between them. And the reason this approximation works well is because at room temperature and pressure, gases are pretty much just isolated molecules with the occasional collision. Now this will break down at higher pressures, and we will talk about one particular correction to that called the van der Waals gas next time. But for the ideal gas, no interactions. And then we will assume elastic interactions with the wall. So pressure in a container is due to the fact that we have collisions of the gas particle with the wall. So we still have the collisions with the wall, it doesn't just pass through the wall, to create the pressure in the container. Then the equation of with the so-called equation of state, which is relating the state variables or state functions, temperature, pressure, volume, and number of moles in this container as one equation, is PV equals nRT. So this is something that you want to get down, and like I say, it will stick with you probably the rest of your life. PV equals nRT. I just want to say a few words on units here. Let's look at this PV term. Let's look at both sides of this equation. So in SI units, P times V is pascals times meters cubed, which is joules. And so this is an energy. So energy on the left-hand side. And the right-hand side is nRT. Well, N is number of moles. R is the gas constant, which in SI units happens to be this number, but the units here are joules per mole Kelvin. So the moles will cancel here, and then times T, nRT, right here, the kelvins will cancel, and we're left with joules energy again. Right, so this is relating an energy to an energy when it's written in this form. Now, of course, we can algebraically manipulate this equation very readily, and that's what's really nice about the ideal gas equation, is that you can solve explicitly for any of these variables very, very easily. And most of the problems that you'll run into in the book when you're practicing this are just having you rearrange that equation and solve for the various components. Now, the SI units are actually not what's used most often when we're talking about gases, because they're fairly inconvenient measurements. We're talking usually in something in the laboratory, we're not usually talking about a cubic meter. So a nice laboratory size is a liter, and then the pressure in our room, in the room pressure, is not very close to a pascal. It's much bigger than that. So we tend to use atmospheres as a pressure. So 1 atmosphere is the pressure on Earth at sea level, which again would be very typical of of a lab condition. So up here, I'm coming to you from Minnesota, we're above sea level. So in our laboratories, we're under 1 atmosphere almost all the time. And well, essentially all the time. And of course, that fluctuates as we have high and low pressure systems come through. But an atmosphere is a good number, and since we're working in different units, our R must take on different units. Now it's liter atmospheres per mole Kelvin, but this is still nonetheless an energy. So liter atmosphere is a unit of energy. And so the unit of energy that's typically used for gases is the so-called liter atmosphere. All right, a while back, quite a ways back, we had talked about intensive variables. These are variables that don't depend on the amount of material. So if I go back and look at my equation of state, my volume is extensive. If I have a piece of something, in this case a gas, and I cut it in half, then my volume is cut in half. Pressure, intensive, but number of moles is extensive. So what we can do is we can divide by number of moles on both sides. So let's go PV divide by N, then the N's cancel on the right hand side, and we get PVM, the molar volume, equals RT. And this is another way you'll see the ideal gas law often, because it's convenient to cast it in terms of only intensive variables. And finally, we can work mass in and then talk about an ideal gas law in terms of density. And so that's what we'll do here. So let's rearrange this ideal gas law into this form. So I'm going to bring the V over here and the RT over there. So I have N over V is P over RT. Then I'm going to swing through and multiply both sides of this equation by the molar mass. So that's grams per mole. And when I do that, I'm going to get grams per mole times number of moles. So I'm just going to get grams or mass. And then I'll have mass over volume, which is density. So this is density. And so this is the ideal gas law in terms of intensive variables, but density. There's a couple of others. We could flip this around and write that in terms of concentration, moles per liter. So maybe that's something you could try. See if you can write the ideal gas law in terms of molarity, in terms of concentration. Okay, so again, practice with this. There'll be a number of problems in your book, whatever book you have, that'll be just working with a pure gas and getting you good at the ideal gas law. Now let's turn to mixtures, because we're going to want to be able to do chemistry in the gas phase, and we'll want to be able to use the ideal gas law when we do that chemistry. So talk about mixtures, and in particular, Dalton's law of partial pressures. And so if we have a container of gas, and it's got a mixture, say A and B, no reactions yet, just A and B in the container, then the total pressure will be the sum of the pressures. And this is Dalton's law, that the total pressure is the sum of the partial pressures. Volume is what it is, and temperature is what it is. That doesn't care about whether we have A and B in here. And total moles, oh, whoops, that should be B. Of course, is going to be the number of moles of A and the number of moles of B. So that kind of is sort of obvious. Why the Dalton's law here? And this can stem back to the nature of an ideal gas. So because the ideal gas has absolutely no interaction, then from an ideal gas perspective, there's no way to distinguish an A from a B. We can label it, and we can think about it, and we can do some chemistry with it, but in terms of producing the results, say for calculating for pressure or temperature or whatever, we cannot depend on the identity of the gas, because the identity of the gas is tied up in how it interacts with itself and other gases. And if there is no interaction, then we will have no dependence on that. Thus, the total pressure must be the sum of the partial pressures. So it's not a proof, but it's one way to kind of rationalize based on what it means to be an ideal gas, Dalton's law of partial pressures. Okay, let's carry this out. Let's write the ideal gas law here in terms of just the total number of particles, right? And again, it's from the ideal gas law perspective, an A and a B are irrelevant, right? Because of no interaction. So then we'll use Dalton's law here, and we'll use the total number of moles on this side. And then we get two parts to this, one that depends on A and one that depends on B. And so we can separate those out and have individual ideal gas law terms. So if we change the amount of A, that will change this term on both sides. And we change the amount of B, that'll change this term on both sides, and they can be independently changed. So therefore, each individual component must itself be a little baby ideal gas law. Okay, now let's look at this ratio here. Let's take the partial pressure of one of those gases over the total pressure. So we can now use these individual gas laws over the total, and we can see that the R, T, and V are the same. And so we're left with just this ratio of moles. Well, that's mole fraction. So we didn't talk much about mole fraction. We talked about it when we introduced the idea of concentration, and then we quickly went to molarity. But mole fraction is an important way to cast concentration. And so we have this ratio equal to each other. So then we can bring the total over, and we can get an expression for the partial pressure in terms of the mole fraction of the gas. And so if we know the mole fraction of the gas and the total pressure, then we know the partial pressure. All right, well, now we could talk about mixtures, Dalton's law of partial pressures, mole fractions, and that sort of thing. So let's do some chemical reactions, and we're going to keep it really simple today. We certainly could involve stoichiometry and grams to moles, moles to grams, and so on, but let's just make it as simple as possible. So let's burn methanol in oxygen to form carbon dioxide gas and liquid water. Let's do this in a 10-liter container, and let's put stoichiometric amounts of reactant. So there's no excess or limiting reagent. So put 1 mole of, make it very easy, 1 mole of methane, 2 moles of oxygen, will be at 298 Kelvin. So we'll use ideal gas law to get the total pressure. Total pressure in here, which will just be N total, RT over V. We work the numbers out, and we get 7 atmospheres. Now, let's go over here to the reactant side. And what we have to notice is that this water is formed, but that's a liquid. So that water vapor is going to condense out into a liquid. And what you'll find, a good thing to do is run this equation for 1 mole of gas, 1 mole of gas at room temperature, and you'll see that, and room pressure, and you'll see that it takes up about 24 liters or so. And so we have 1 mole of gas will take up about, let's just call it 20 liters. And so I'll write that down. A little more than that, but about 20 liters at SATP, standard ambient temperature and pressure. 1 mole of water, liquid water, takes about 18 milliliters. So let's call that 20 milliliters, right? Because it's 18 grams per mole, and and then the density of water is 1 gram per milliliter. And so we have about 1,000 times less volume when we condense water vapor, 1 mole of water vapor into 1 mole of water liquid. Notice I didn't have to say 1 mole of water here because it doesn't matter what the identity of the gas is. So 1 mole of water vapor will take up about 20 liters. 1 mole of water liquid will take up about 20 milliliters. So in terms of the size of this container, the amount of water that's sitting on the bottom is not going to change the volume available to the gas in any appreciable way. So we can just assume that we still have 10 liters of volume, and our only gas in there is the carbon dioxide. And so we do our moles to moles from the stoichiometry. We will produce 1 mole of carbon dioxide. Work that out, we get 2.4 atmospheres, and then we can, I'll put P reaction, delta P reaction, and that should be a minus here because we are decreasing the pressure. So we see here that we get a change of pressure in the vessel because of the reaction. Now, we kind of needed this back when we talked about Le Chatelier's principle. And so now we can kind of think about this in terms of Le Chatelier's principle. So if we were to increase the pressure, right, we can relieve that pressure, we can relieve that disturbance or mitigate that disturbance by having the reaction, in this case, go forward to reduce that pressure. And so here we can really see now what we sort of just took earlier in the course when we were talking about Le Chatelier's principle and gases and increasing pressures. So there'll be another big section in your book. It'll have plenty of problems that deal with ideal gas law in the context of chemical reactions, also ideal gas laws of just mixtures with no reactions. So again, I'm going to let you be on your own here. I think a good advice here would be to pause going through these videos for a few days until you really have worked through a lot of those problems and feel really good about them. Then pick up with the next lecture, which is going to be on a non-ideal gas called the van der Waals gas.